We take it for granted now, right? Like asking an AI a question and getting a pretty insightful answer, or having a back and forth voice conversation that sounds like you're talking to a real person.
It really is incredible how far things have come, even in just the last few years.
It is, but what I keep thinking about is, what's the next frontier? What's after text and voice?
Oh, I know where you're going with this.
I'm talking about lifelike video communication, like truly believable digital humans that can hold a conversation with you face to face, not those kind of stiff, uncanny valley avatars we often see.
You're talking about avatars that can really convey emotion, that react naturally, just like another human would.
Exactly. And that's what we're diving into today. Some really fascinating research coming out of Alibaba's Tiny Lab.
You sent over a really interesting paper, ChatAnyone, stylized real-time portrait video generation with hierarchical motion diffusion model. Quite a mouthful.
It is.
But your notes on it were super helpful, really helped me get my head around it. And I think our goal today is to pull this apart and understand what makes ChatAnyone tick, especially how it's pushing the boundaries of generating realistic and expressive portrait videos in real time.
Yeah, and to me, that's the exciting part, right? Moving past those avatars that are close to human, but still have that something not quite right feeling.
You get that unsettling sense in the uncanny valley?
Yes. And the ChatAnyone researchers, they're not settling for that. They're going for something much more nuanced, more subtle. It's not just the head movements, but think about those slight shifts in posture, the natural flow of language, even the hands, all the things that make human communication feel so authentic.
Absolutely. It's thinking about all those details, the hands especially, that's been a real challenge in this field.
It has. But as we move towards these richer digital interactions, getting that level of detail is crucial.
Couldn't agree more.
Okay, so let's maybe rewind a bit. Let's talk about where previous attempts at this, generating lifelike video where they're falling short. What were the big limitations they were hitting up against?
Yeah, so earlier methods, particularly the ones using GANs, generative adversarial networks, they made progress, don't get me wrong. Like lip syncing got better, basic head movements, all that. But they were running into these fundamental roadblocks.
What kind of roadblocks?
Well, a big one was getting the head and the rest of the body to move naturally together. You'd often see this disconnect. The face might be doing its thing convincingly, but the body would be stiff, almost robotic.
Oh, I see. Like a really expressive head glued to a mannequin.
Exactly. It totally breaks the illusion,
And it probably contributes to that uncanny valley feeling.
for sure. Another challenge was how do you get really fine-grained control of those facial expressions?
Like the intensity of an emotion, the subtle differences, the styles.
Exactly. Existing models were kind of blunt instruments. They just couldn't capture that level of nuance. And then, of course, there's the hand problem.
Yeah, the never-ending quest for convincing digital hands.
It's hard. Hands are so complex, so many joints. They're always occluding each other, getting the textures right, the movements. It's a nightmare for computer graphics.
A nightmare. I remember from the paper, though, wasn't there also an issue with the computational demands of these newer models?
Oh, absolutely. That's a really important point. As these models get more expressive, especially with the rise of diffusion models, which are amazing for quality and diversity, they become incredibly computationally intensive.
So they need a lot of horsepower to run.
A ton. And that's because diffusion models work by basically starting with random noise and then gradually refining it step by step into the desired output. It's this multi-step denoising process, which takes time, and time is the enemy of real-time interaction.
Right, because if there's too much lag, that natural flow of conversation breaks down. It's not real time anymore.
Exactly. So you have all these amazing techniques, but getting them to work smoothly and quickly enough for a real conversation, it's been a huge challenge.
Okay, so ChatAnyone steps into this arena, and it's got this two-stage framework that's tackling all these problems head on.
It really is a clever approach.
So let's break it down. Let's start with that first stage, what they call the hierarchical motion diffusion model. What's going in and what's the goal here?
All right, so the input to this first stage is actually pretty straightforward. It's just an audio sequence, the speech that you want your digital human to speak.
Okay, so that's simple enough.
Yeah. But the output, that's where things get a bit more sophisticated. Instead of directly generating video frames, this stage is predicting the control signals that will drive the motion of both the face and the upper body.
Control signals, meaning,
Meaning it's figuring out how the face should move the lips, the jaw, even subtle things like eye and brow movements in response to the audio. But here's the really clever bit. It's doing this in a hierarchical way.
hierarchical as in,
It first predicts the facial motion, okay? And then it uses those predicted facial motions to help predict how the upper body and hands should move. It's basically saying, okay, the head's doing this, so how should the rest of the body react naturally to that?
that makes sense, right? Because in real life, how we move our head often dictates how we move the rest of our body. It sets the tone for the gesture.
Precisely. Think about how tilting your head can completely change the way your shoulders move, how you hold your arms, everything.
Totally. So ChatAnyone is building this awareness of natural human behavior into the model.
It is, and this hierarchical approach to predicting motion, recognizing that the head kind of leads the way, it's a big reason why ChatAnyone is able to create more natural-looking animations. It's one of the key innovations here.
And it's like it's a much more elegant solution than trying to predict everything all at once.
Oh, absolutely. Trying to predict the whole body's motion in one go from just audio, that would be incredibly complex. This hierarchical method breaks the problem down into more manageable chunks.
Now, you mentioned earlier that this model uses both explicit and implicit motion representations.
Yeah, another cool thing they're doing.
Can you explain what those are, and why is it important that they're using both?
Sure. So explicit representations, those are basically predefined controllable parameters that describe motion. Like for the face, they're using something called a 3D morphable model, or 3DMM for short. Think of it like a template of a human face that you can adjust with different parameters. Like if you want to make the digital human smile, you can tweak the smile parameter in the 3DMM.
Okay, so it's very direct, very controlled.
Exactly. It gives you a lot of precision. Now, for the body and the hands, they're using things like body templates and a really detailed hand model called Mano. These are all explicit representations, giving you a structured way to control specific features.
But what about implicit representations? How are they different?
So implicit representations are less about defining things explicitly. It's more about learning patterns from data.
Okay, so it's letting the model learn from examples instead of hand coding everything.
You got it. For the body, ChatAnyone uses these learned implicit key points that can capture more subtle, nuanced movements that might be hard to define explicitly. And for the face, they've got this cool idea called key point displacement. It's basically an offset that you add to the existing explicit 3DMM key points to capture even finer detail like tiny wrinkles or individual muscle twitches.
So it's like adding another layer of expressiveness on top of the basic template.
Exactly. It's about getting that epic level of realism and personalization. And what's really important here, academically speaking, is that they recognized you need both. You can't just rely on predefined parameters or just learned features. You need that blend of control and flexibility to really nail those subtle details that make human motion so complex.
That makes a lot of sense. Like you need the structure of the explicit, but then you need the implicit to add that touch of life, those little imperfections that make it feel real.
Exactly. And that's a big contribution of this work, highlighting how crucial that balance is.
Now, another thing that really stood out to me was this idea of fine-grained expression control and even style transfer. How are they achieving that kind of personalization?
So for that, they're using some really neat techniques. One is called adaptive layer normalization, or ADLN. Basically, it lets the model take information about how intense you want an expression to be or what kind of pose you want, and then it uses that information to adjust the strength of the movements generated.
So you could basically dial up or dial down the expressiveness.
You got it.
That's so useful, right? Because you wouldn't want the same level of expressiveness in a casual chat versus a more formal presentation.
Right. You might want to tone it down a bit in some contexts. And for style transfer, like if you want to mimic how a specific person expresses themselves, they can actually use reference videos. They take those videos, extract the facial expressions, and then use that information to guide the model to generate motion in that particular style.
So the model is literally learning from examples, watching how someone else emotes, and then trying to replicate that.
It is. It's pretty amazing, and it's a huge step towards creating those truly personalized, believable digital avatars that we were talking about earlier.
It sounds like it. Now, last thing on this first stage, I remember them mentioning something about a diffusion transformer network. What's that all about?
Yeah, so that's the architecture they're using to actually learn those motion patterns from the audio and the historical data. And transformers are really good at handling these long-range dependencies in data, meaning they can figure out how the audio at one point in time relates to how the face and body should move later on.
So they're making those connections over time, figuring out the cause and effect.
Precisely. And that's crucial for getting those smooth, natural transitions between movements. It's not just about reacting to the current sound, it's about anticipating what's coming next and making those subtle adjustments that we make naturally as humans.
Okay, so that's a lot to unpack just for the first stage. It predicts all these nuanced motion signals, and it can even personalize them based on style. Now, let's talk about stage two, what they call the hybrid control fusion generative model. What's happening here?
So the second stage is all about taking those motion signals from the first stage along with a single portrait image of the person and turning that into actual photorealistic video frames of the upper body in motion.
Okay, so it's finally generating the visuals.
It is, and the way it does this is through a warping-based GAN framework.
Warping based, so it's not generating each frame from scratch.
You got it. It's actually more efficient than that. Essentially, it's figuring out how to deform or warp the features of that initial image to match the predicted motion. It's like a digital puppeteer moving parts of the image around to create those new poses and expressions.
Oh, I get it. So it's like taking a still photo and then stretching and morphing it to match the movements.
Exactly. Much faster than trying to paint a whole new picture every frame.
That makes sense, especially if you're trying to achieve real-time performance.
Absolutely. So this warping-based GAN framework, it has a few key parts. First, it extracts appearance features from that original image and motion features from the first stage. Then it estimates what they call a warping field. That's basically the map that tells each part of the image where to move. And finally, you have a generator network that takes all of this information and creates the final photorealistic image frame.
And this is where that hybrid control fusion idea comes in again, right?
Yes, just like in the first stage, they're using both explicit and implicit control mechanisms. So the warping process is being guided by those precise facial landmarks from the 3DMM, but it's also being influenced by the more implicit body key points that ensures that both the big overall movements and those subtle facial details are captured accurately.
Now, we talked earlier about how hands are so hard to get right.
The bane of computer graphics.
So how are they tackling that specific challenge in this second stage?
Okay, so this is one of the really cool technical innovations here. They actually have a separate step called explicit hand control injection.
Okay, walk me through that.
So they basically take the Mano hand model, which is incredibly detailed, and they render out 3D images of the hands in the exact pose that they need. Then they inject those hand images directly into the generator network at multiple scales using something called adaptive instance normalization, or EDAIN.
So instead of just hoping the AI figures out the hands on its own, they're giving it explicit instructions about how the hands should look.
Exactly. They're saying, hey, here's exactly what the hand should look like in this pose. Now go and generate the rest of the image around it.
And why is that so important for the hands specifically?
Because hands are so complex, right? With all the joints and the way they include each other, it's really hard for an AI to just infer that from general body movements. By giving it those hand images directly, they're giving the network a much better starting point, and it can generate much more realistic hand movements and textures as a result.
It's like giving the AI a cheat sheet for the hands.
In a way, yes, and it works remarkably well. Now, another clever thing they've done is they've added this face refinement module.
What's that for?
Well, think about it. That initial image they're using, it might not capture all the nuances of expression that they need.
Right, like if the person wasn't smiling in the original photo.
Exactly. So this face refinement module is a separate little network that specifically enhances the facial details and makes sure everything blends seamlessly with the newly generated upper body. It's driven by those explicit head key points, but it also uses those implicit offsets to capture those finer details. Remember those?
Yeah, the ones that add that extra bit of nuance.
Yep. And here's a really cool detail. The input to this refinement module actually includes the cropped background around the head, but with the face itself masked out. So it's focusing on generating those new facial details and making sure they fit naturally within the context of the surrounding image.
That's really smart. So it's not trying to recreate the whole head, just the parts that need to change.
Exactly. And finally, to make sure all these pieces are working together harmoniously, they use these cascaded loss terms during training.
Lost terms meaning.
It's how they guide the learning process, how they tell the model, hey, you're doing well, or nope, try again. They have standard image generation losses, but also specialized ones, like a perceptual loss that focuses specifically on making sure the hands look high quality, and a landmark loss that helps to fine-tune the position of those implicit key points.
So it's like a whole orchestra of feedback signals, each one focused on optimizing a different aspect of the system.
It is, and that's why they're able to get such impressive results.
Okay, so we've got this sophisticated two-stage system that predicts motion in a really clever way, then generates the photorealistic video using warping and refinement with special attention paid to getting those hands and faces right. But how does all of this perform in real time? Because that's a huge factor here.
Right, that was one of their big goals, to make all of this fast enough for a real-time interaction.
And did they pull it off?
They did, and this is a big deal. They report that ChatAnyone can achieve speeds of up to 30 frames per second at a resolution of 512 by 768 on a single high-end NVIDIA RTS 4090 GPU.
Okay, so that's pretty darn fast. And that resolution, that's good enough for a smooth, clear image, right?
It is. It's what you'd want for a video call, for example. So they've hit that sweet spot of quality and speed, which is really impressive given how complex this model is.
Yeah, that really is a testament to the engineering that went into this. And they also talk about the extensibility of their framework. What do they mean by that?
So they designed ChatAnyone in a very modular way, which means you can choose which parts to use depending on your needs. So let's say you just want a simple talking head avatar, you could just use the head motion and face generation parts. But if you need a more immersive experience with the whole upper body and hands, you can use the full system.
So it's like a build your own avatar kit. You can choose the level of detail you need for the task at hand.
Exactly. And that makes it much more practical for real world applications. You're not stuck with one size fits all.
And as with any good research, they did a ton of experiments to see how well all of this actually works.
Oh, yeah, they really put it through its paces.
So what were the results? How did ChatAnyone stack up against other methods out there?
Well, for video generation, they tested it in a couple of ways. First, they did something called self-driven reenactment, which basically means they took a still image and animated it using the motion from a separate video.
Okay, so it's like taking a photo of someone and then making them move like they're in a different video.
Right, and they compared ChatAnyone to a bunch of other state-of-the-art methods, both GAN-based and diffusion-based, using a whole battery of metrics like PSNR, SSM, and LPIPs for image quality, FID and FAD for overall video quality, and then some really specific ones like CSM and HKC to look at how realistic the features were, especially the hands.
And how did it do?
It blew the older GAN-based methods out of the water, especially when it came to generating upper body and hand movements. That explicit hand control was a game changer. You could really see the difference in the visuals, too. The hands were just so much more detailed and believable. And when they compared it to the newer diffusion-based methods, it got comparable results in terms of overall quality. But remember, it's doing this at a much faster speed because it can run in real time. So it's kind of hitting that sweet spot, high quality, without sacrificing the speed needed for a real-time interaction.
Bridging that gap between quality and speed, that's huge.
It is. And they also specifically looked at how well it performs for generating talking head videos, which is obviously a big application for this kind of technology.
So did they get good lip syncing, believable expressions, all that?
They did. For that, they compared it to some other established talking head methods like Sad Talker and Annie Talker. And on top of those regular image quality metrics, they used some special ones too, like sync to measure how well the lips were synced to the audio, and diversity to see how varied the facial expressions were.
And how did it do?
It consistently scored better on those lip syncing and expression metrics. ChatAnyone was just more accurate and more expressive, and they attribute that to that hierarchical motion diffusion model. It's just better at capturing those nuances in speech and translating them into believable facial movements.
So it's not just moving the mouth, it's understanding the emotion behind the words and conveying that through the face.
Exactly, and it really shows in the results. They also did some ablation studies, which are basically like playing a game of what if with the model.
So taking pieces out and seeing what happens.
Exactly. They wanted to see how each component of ChatAnyone was contributing to the overall performance. So they looked at the impact of the style transfer, the hybrid control, the hand control injection, and that face refinement module, each one separately.
And what did they find? Were those components really making a difference?
Oh, absolutely. Like when they took out the style transfer, the facial expressions weren't as similar to the reference videos. When they removed the hybrid control, those finer details in the facial expressions got less accurate. And when they took out the explicit hand control injection, well, that had a huge impact.
Like the hands went back to being a mess.
Pretty much. The realism of the hands and the overall image quality took a big hit. And removing the face refinement module led to some noticeable dips in the visual quality of the face. Things just didn't blend as smoothly.
So those carefully designed components, they're really doing their job.
They are, and the ablation studies really prove that it's not just one trick, it's all those innovations working together, the hierarchical motion prediction, the hybrid control, the hand and face modules. That's what gives ChatAnyone that edge.
Okay, so big picture time. For everyone listening, what are the key takeaways from ChatAnyone?
I think it's safe to say this represents a huge step forward in creating those truly believable, responsive digital humans and doing it in real time. It's not just making an avatar talk. It's about giving it that believable presence through natural body language, nuanced facial expressions, and those details like the hands, all powered by this really clever, innovative tech.
And from a research perspective, you said those innovative points are really what sets this work apart.
They are that hierarchical approach to motion, mimicking how humans actually move, the clever mix of explicit and implicit control for both the face and the body, and those dedicated modules to crack the hand and face realism problem. Those are huge academic contributions.
And the potential applications of all this? Wow. Think about video conferencing, making those interactions more natural and engaging. Virtual avatars in the metaverse, augmented reality, all those areas could benefit from this. Imagine interacting with a virtual being that responds to you with all those subtle cues that a real person would.
It's really exciting to think about.
It is. And if we zoom out even further, it's about making our interactions with technology more intuitive, more seamless.
Imagine virtual assistants that can really understand and respond to our emotions, or educational tools that are so engaging they feel like you're learning from a real person. And in those virtual worlds where so much of our communication is nonverbal, that's where this kind of technology could really shine.
So as digital humans keep getting more sophisticated, more expressive, more real-time, it begs the question, how is this going to change the way we connect and interact with each other in the digital space?
I think that's a question we're all going to be grappling with in the coming years. It's a fascinating time to be working in this field.
It is, and for anyone who wants to dig deeper into the nitty-gritty details of ChatAnyone, you can probably find the paper and maybe even a GitHub page with some code and supplementary materials. Just search for ChatAnyone stylized real-time portrait video generation and you'll be off to the races.
It's definitely worth a read. It's a really exciting glimpse into where this field is headed.